Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about density functional theory and derive the Hohenberg-Kohn theory on which density functional theory is based. Classically, when we talk about a system, we can define its state or the microstate by the positions as well as the momenta of all atoms, of all particles. So we have 6n coordinates given by a real number for n particles. In quantum mechanics, we define a state by a state vector or a wave function R1 to Rn. That wave function is antisymmetric, or the state vector can be given on a basis of many particle states with prefactors which are complex numbers, and the many particle states can be written as single Slater determinants where you create n particles in a subset of basis functions. And the problem is this grows exponentially with the number of particles and thereby making the wave function an object that is not, one cannot really write down for microscopic systems. There is another way in quantum mechanics to address or classify the ground state, and that is done in the Hohenberg-Kohn theorem. And that states that our ground state is defined by the ground state density. So knowledge of the wave function with 10 to the 23 particles for a solid gives you equal information as knowledge over the density, whereby the density is given as the number of particles times n minus 1 integrals over the coordinates 2 up to n of the norm of the wave function squared, R2 up to Rn. Or in second quantization, that is the sum over two of your single particle basis functions, and then the expectation value of the creation and annihilation operator for the ground state multiplied by the one particle wave functions, complex conjugated and normal. That of course is a huge reduction in information content. And the Hohenberg-Kohn theory tells you that knowledge of the density for the ground state is equal to the knowledge of the wave function. Or in other words, when I know my density, I can rederive what my wave function is for the ground state. And observables can be determined from the density, whereby the density itself is an observable with the use of functionals. So for any observable, for example the ground state energy, you can define a functional as a function of the density. So if you know that functional for a given charge density, you then can calculate the ground state energy. The reason that we don't use density functional theory is that this functional can become arbitrarily complex, and we only know utterly impractical functionals or approximate functionals. And approximate functionals are very much used. Basically all high accurate calculations that we do at the moment in condensed matter or chemistry are based on these kind of functionals in density functional theory. So let us first prove the Hohenberg-Kohn theorem, that indeed the density alone is enough to represent a quantum system in its ground state. By the way, Kohn got a Nobel Prize for basically this. So the idea of the theorem is that we are going to derive the Hamiltonian from the density and the wave function from the Hamiltonian. And when we have the wave function, the system is uniquely determined, because that's how we defined previously a quantum state. So if I can show that the density uniquely defines a Hamiltonian, and we know that a Hamiltonian uniquely defines a ground state, then we are able to show that from the density we can uniquely define a wave function, and with that there is a unique value for all observables that we can measure or calculate. When we do this, we can look at our Hamiltonian, which is given as a sum of the kinetic energy plus the potential energy plus the Coulomb interaction. And I'm going to use here the letters used in the literature for density functional theory. So T for the kinetic, V for the potential, and U for the Coulomb, where T is the sum over all atoms minus h bar square over 2m gradient. V is the sum over I potential, and U is a half sum I is not j 1 over 4 pi epsilon 0 e square Ri minus Rj. Now all systems that we are interested in have the same form of the kinetic energy for the Hamiltonian and the same form of the Coulomb energy of the Hamiltonian. So the question is, if we want to distinguish systems of interest, can we determine the potential Hamiltonian from the density? So we need to prove that rho determines V uniquely. And the way we do this is by contradiction. So we're going to assume that we have a single density that is represented or can represent two different wave functions with two different potentials and therefore two different energies. And we'll show that if we assume that as long as these energies or potentials are different, you will get a contradiction. So the first energy is E1, which is the energy of the ground state psi1 for Hamiltonian 1. And we can write this as the sum of the potential energy of potential V1 plus the Coulomb and kinetic energy, kinetic and Coulomb energy. And the potential energy we can write in terms of densities, and this is rho 1 for the first state, plus then of course still the kinetic and Coulomb interaction. Now we have a second state that I'm going to first assume to be different from our ground state. So it is not equal, or to a first state, so it's not equal to a phase times the first state, not equal. And I'm going to assume that H2 psi2 is E2 psi2 and we're going to assume that rho 1 of R is equal to rho 2 of R, which we can then also call just the density. So let's show that if this is true and that is true, then we get into a contradiction, and therefore these have to be equivalent when the densities are equivalent. And both of them are ground state wave functions. So as these are ground states, first of all, we can of course write down the same equation as we had for E1, but now for E2. The energy is the potential energy plus psi2 kinetic plus Coulomb psi2. Now I know psi1 is the ground state of Hamiltonian 1. I also assume that I have no degeneracies. This is in the original proof assumed. Later it has been generalized to also include degeneracies, but if I prove it for a system that is non-degenerate, then I hope you believe me that one can generalize it. And that means that if I take an arbitrary other wave function, then the energy of that wave function is always bigger than the ground state. Well, psi2 h1 psi2 is integral v1 of r rho 2 of r dr plus psi2 t plus u psi2. Now this can be written as E2, and then we have plus the integral of v1 of r minus v2 of r times rho of r dr. So E1 is smaller than E2 plus this integral over the difference between the two potentials times the density. We can do the same when we start with E2, that must be smaller than psi1 h2 psi1, as E2 is the ground state energy of the Hamiltonian 2, and this is E1 plus the integral v2 of r minus v1 of r times rho of r dr. We can now sum these two equations, and what we get is E1 plus E2 is smaller than E2 plus E1, and here we have V1 minus V2, there V2 minus V1, so that is 0. What follows is that if we assume that two wave functions are different but their densities are the same and they are the ground state of an Hamiltonian, then these energies are smaller than themselves, and therefore that leads to a contradiction. So it is not possible that these wave functions are different but have the same density when they are representing the ground state wave function. Or in other words, the density uniquely determines the ground state wave function. And now you also immediately see that we haven't told you how it determines it. We just say that it must be uniquely given by it, otherwise we get contradictions. Well, how can we determine the ground state density? And for that we know that we can define an energy which is a functional of the density, which is an energy functional. Of the density. That's where the names come from, density functional theory. All observables become functionals of the density. Now, rho of r for the ground state must be the density that minimizes the energy. So again, we're looking for an extremum that, if we knew are functional, that defines an energy with respect to some density, then we have to minimize our function rho to find the ground state. But that of course leaves the question, what is our functional? And this is still an open question in density functional theory. It's often stated that we do not know an exact functional. The more precise definition is that we do not know useful or functionals that are exact or functionals that are calculatable. So let me present you a useless but exact solution. For the density functional, we can define a set of functions psi tau of coordinates 1 up to n for n particles that are antisymmetric and normalized. Then from this function we can define a density So we want to define all functions of this form, which of course is an infinite set. And we define the density, as we normally do, R2 up to Rn, norm squared dr2 up to drn. Now some of these functions will give the same density. That's perfectly fine. What we have showed is that for the ground state, a density uniquely defines the state. That doesn't mean that there might not be other excited states with the same density. So we can now say that the energy functional with respect to this density is the energy of that state. And of course there are many functions that will give you the same density. So we want to have the ground state, so we take the minimum with respect to all different functions that define that density. So we can look at all possible functions, calculate the density, then all functions that give the same density, we calculate the energy, and the energy that we give to a density in our functional is then the minimum of that set. Well, this is worse than just calculating the eigenstates, because you do have to calculate all many-body functions, and you then have to look at the densities derived from that. So normal, solving the Hamiltonian in the standard way is more compact than doing density functional in this way. But this is the useless but exact solution. What we will do in further lectures or in further videos is have a look at approximate solutions for the functional. And that's where then also the term mean field will come in. This functional is exact and not a mean field solution, whereas the functionals that we will talk about later, after we introduced Cauchy orbitals, actually can be mapped to mean field models and define effective orbitals, often called or one particle states often called Cohen-Sham orbitals, defining some quasi-particles that move in an effective potential. So far so good. We've shown you that we do not have to work with wave functions, but in principle we can work with densities. That's of course an extremely compact method to represent your many-body state that does not grow exponentially with system size. The problem is that we have to then find a functional that calculates the energy from that state, and the exact functional does scale exponential with system size in steps in between. But we can now have a look at approximate functionals to see how far we get. Thank you very much for your attention. We see each other in the next video. Stay healthy.